And so our next talk is Mathias Sonnleitner from Münster, who is going to tell us about entropy numbers of finite-dimensional Lorentz space embeddings.
Thank you for the introduction, and I also want to thank the organizers for giving me the opportunity to talk about my findings jointly with Joscha Pochner and Jan Wibrel on entropy numbers. So entropy numbers already appeared in yesterday's talk by Igor Kosov, but I want to introduce them in the following slightly more general way. So I want to consider continuous embeddings between quasi-binary spaces. And basically this corresponds to the approximation problem where you want to approximate uniformly in the unit ball of a quasi-binary space in a quasi-norm Y. And for number k, we define the dyadic entropy number as follows. So we look at the minimal radius we can take so that we can cover our unit ball Vx by copies of the rescaled copies of Vy, namely 2 to the power k minus 1 copies. And maybe several facts. So the first entropy number measures the size of our embedding, so the norm of the embedding up to a constant, where Cy is the quasi-norm constant of Y. And in the case of a compact embedding, the entropy numbers converge to 0, and actually they provide a means of quantifying the degree of compactness of our embedding. And via Carr's inequality, one can obtain lower bounds on Gelfand widths and thus also on general approximation algorithms using linear information. And this relation actually was already used by Donoghue in his paper on compressed sensing in 2006, where he also applied Carr's inequality and lower bounds on entropy numbers, but unfortunately Carr's inequality was not known to be true in the quasi-Banach space setting and was only proven later by Hinrichs colleague Wibrel in 2016. So this provides us with some motivation to study these entropy numbers for general embeddings, and I want to focus on Lorentz space embeddings here. And before I present Lorentz space embeddings, let me focus on the more classical case of LP space embeddings, which are often considered and which is a very nice result. So for P, general P between 0 and infinity, we consider classical LP space finite dimensional, and then we have the following result due to Schütt in the Banach space case 84, an upper bound in the quasi-Banach space case by Edmonds and Triebel, and then independently at the completion and extension to a full setting by Guidon, Litvak, and Kühn. And here we have these two different regimes depending on whether R is smaller or larger than P. And in the first regime, in this year, we have the following behavior, where this notation indicates lower and upper bounds up to constants which are independent of k and n and only depend on p and r. And we notice here this exponential behavior. And here in this other case, we have these three different regimes depending on whether k is smaller equals logarithm of n, whether it's larger than the dimension, or in between. And actually this case in between is the interesting case I will later focus more on. And we will see similar results if we look at more general embeddings, Lorentz spaces. And here these three different regimes roughly are explained as follows. So the first regime corresponds to the norm of the identity, the size of the identity. And so E1 is corresponds to the size of identity. Here this large regime, this corresponds to volume asymptotics. And in between, this is the interesting interpolating regime. And here these three regimes coincide. And this is very classical LP spaces. So what other spaces can we look at? So natural generalizations of LP spaces are, for example, Wallich spaces or mixed Lebesgue spaces. These were studied by different authors already. So we decided together with Dr. Brochner and Jan Weberel to look at Lorentz spaces, which form yet another generalization of LP spaces. And they are defined as follows. So we have two parameters here, and we define the Lorentz quasi-norm as follows. So we look at the non-increasing rearrangement of the absolute values of our vector. So we order them in a decreasing way, and then we weight them and consider LU quasi-norm. And this gives us a finite-dimensional Lorentz space, which is a quasi-norm space, and quasi-Banach space also if we put n equals to infinity, and in a special case parameters 1 smaller equal u, smaller equal p, we obtain a Banach space. And here we have a picture of a unit ball. So in the case of u equals 1 and p larger than 1, it looks something like this. So you can imagine it as follows. You take an LP, L1 ball in this case, LU ball. Then you weight the coordinates differently according to this polynomially decaying sequence. And then you permute over all coordinates and intersect the result. And this is what you get. And in fact, the special case u equals p, you obtain the LP spaces. This is why they are generalization. And in fact, they interpolate between LP spaces. So you obtain the Lorentz spaces by real interpolation from LP spaces. And also this property makes them very tractable with respect to entropy numbers or other S numbers, because you have interpolation properties. And another special case, u equals infinity, yields the so-called weak LP spaces, which are also used in compressed sensing. You know something about your signal, that it decays, for example, in some basis as a polynomial. And in fact, Lorentz spaces were also used by Edmonds and Netrosov in 2011 to disprove a two-sided interpolation conjecture on entropy numbers. So entropy numbers you can interpolate on the one side, x, or on the y, but not on both together. And Edmonds and Netrosov looked at diagonal operators between Lorentz spaces to show this result. So, in fact, what one do we want to look at here? So we consider now two different n-dimensional Lorentz spaces, parameters p, q, u, and v, and we want to investigate the behavior of the entropy numbers up to, again, constants which may depend on these four constants here. And the previous work is as follows. So Edmonds and Netrosov 1908, so it was not clearly written there, but in fact you can obtain via an interpolation methods that if the parameters p and q are different, then you come back to the setting of LP embeddings. So nothing interesting happens there in this case. And it was then only in 2020 that Dolezhalova and Weberel looked at another regime and could obtain interesting results there, namely the case of when p equals q equals v, all between 0 and infinity, and u equals infinity. And I want to present their result and the general case as we obtained it. So we obtained the behavior in all for all different choices of parameters. So first p not equal to q, then we have different cases. So I will present them to you now, what can happen here. So first of all, we look at the following choice of s, so integer which is of order k divided by log n over k plus 1. So this already appeared in the behavior of the entropy numbers for LP spaces in this interesting range. And if we take this S now and look at the following cases, so case 1, p is equal to infinity, we obtain this uniform behavior. So q equals infinity, we obtain these three different cases here with logarithms of S here. Then we have the following cases when p is equal to q but smaller than infinity, then it distinguishes between u larger or smaller than u. So we have really a rich behavior here. And we have here this is the case which was obtained by Dolezha, and Vibral. And then even one more case when P is equal, Q equal infinity. I'll briefly only show you these slides to indicate how rich the behavior between of the Lorentz of the entropy numbers of Lorentz space embeddings is. So you see a lot of different things happen here, and maybe I only explain a little bit the background and the techniques behind these results. And in fact, so I explained these three different regimes. The norm of the identity matters where we have volume asymptotics, and here the interesting regime. And I want to present this in a slightly more general way, so not only for Lorentz space embeddings, but for n-dimensional quasi-Banach spaces. And we look at the following definitions. So we need some assumptions on our quasi-Banach spaces, which will be satisfied by Lorentz spaces. So first of all, they should have a basis which is symmetric, meaning that essentially the norm of an element only depends on the non-increasing rearrangement. And we want to have the following monotonicity property, namely if we have coefficients and if we increase the coefficients in absolute value, then also the norm, quasi-norm, should increase up to a constant. And it was assumed in a paper, and we were not clear about this, whether symmetry implies monotonicity, but yeah, this is true for X-Banach space, but probably false in general. We only conjecture this, we don't know. Maybe if you know some related work, yeah, we would be grateful for knowing this. But so in general, we have to assume both symmetry and monotonicity. And if we do this and look at the large K regime, so the volume regime, we obtain the following, namely the entropy numbers. They can be characterized by the coefficient of the volume, so the volume ratios in some sense of the quasi-Banach space unit balls. Or one can also equivalently state it via the fundamental functions, which takes the basis vectors, sums them, and computes the norm. And this was already known for the Banach space case in the same paper by Carsten Schütt. And now we also know it for the quasi-Banach space case, but only with this additional monotonicity assumption. And then the interesting regime is characterized by best S-term approximation numbers, as we shall see in a moment. And for this, I want to introduce error of best S-term approximation of an element in a space X, and we look at the best approximation in the Y quasi-norm by elements which have at most S non-zero entries. And for example, if Y is L infinity, then we obtain the non-increasing rearrangement. And this is in fact strongly connected to Lorentz spaces, but best S-term approximations, as we have seen throughout the week already, play an important role for approximation or bounds on entropy numbers algorithms. So yeah, also previous bounds for the LP, for the classical case, were can be given in terms of S-term approximation numbers. And I want to mention here this interesting result by Temlekov, namely if we have the Banach space case, so if you have a norm. So in fact, I only cite here the special case. And if we have decay of the supremum over the unit ball of these numbers, then we can obtain decay of the entropy numbers. But yeah, with this special S, and this explains already part of the results in the LP case. And in fact, under our assumptions of symmetry and monotonicity, we can obtain even more, which was quite surprising to us. Namely, can obtain, if we have now two Banach spaces with the same symmetric Banach basis, that the entropy numbers are really characterized in the smaller than n regime by the S-term approximation numbers by the supremum. And S is again minimal integer such that this holds. And moreover, we can even say that the best S-term approximation numbers, they exhibit regular decay. And this follows, in fact, from results due to Edmonds and Nitrusov from '98, which were kind of hidden. So I talked to Thomas Kuhn, and he also was not aware of the results which were there before he wrote his paper on entropy numbers, because with the results from Edmonds and Nitrusov, one can also obtain LP case. And Edmonds, Nitrusov, they in fact considered this quantity here. So this is not precisely the best S-term approximation of a signal, but the following. So if we have a signal like this, for example, order like this, then we would do the following. So we form the minimum of the S largest and the I largest. So we replace the signal on the S largest coordinates by the S largest. So we cut off in this way, and the remaining part remains the same. Then we compute the Y quasi-norm of this. So this will correspond to this quantity here. And best S-term approximation would mean that we approximate by a vector which has the S largest coordinates here. So we would obtain this signal here. So these are different, but in fact, under the symmetry and monotonicity assumption, the order of decay is the same for these two quantities, up to, again, constants which are independent of S and the dimension n. And for this quantity, already Edmonds and Nitrusov, they obtained some nice results, and we could use them and obtain this interesting behavior for best S-term approximation numbers, which translates to the entropy numbers in this way. And with this, I want to thank you for your attention.
Questions? This result also holds for n going to infinity, right? There's no.
Yes,
n
so this is independent
so.
of n. Yes.
Pretty good, thanks.
Any other questions? Okay, no, let's thank our speaker again.